NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, and welcome to another edition of the 2021 Von Karman Lecture Series. I am Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for our topic this evening, an Earth Day special, Science on Ice, What Ice Says About Past, Present, and Future Climate. Earth's ice is both beautiful and awe-inspiring. Ice and the melting of glaciers and ice sheets are both a predictor and an observable part of Earth's changing climate. Using ice cores and radar technology to see deep into Earth's ice, scientists can learn more about our planet's past. NASA, JPL, and Caltech are working to understand more about these changes, how to protect our Earth, and to share it with you. Joining us as co-host this evening is Jocelyn Argueta. Jocelyn is a public outreach specialist for NASA's Earth, where she shares stories of how NASA data helps us learn more about our home planet. Hi, Jocelyn. Thanks for joining us.
Hi, Nikki. I'm so excited for the talk tonight and for all of the questions that are being submitted by our viewers at home. So as always, we'd like to remind everyone that this is your space program and we want you to be involved in the conversation. So please add your questions to the chat and our amazing social media team will pass them along to us. We'll do our best to answer as many of your questions as possible, but if you don't see the chat, just refresh the page and it should be there.
Awesome. Thank you so much, Jocelyn. As always, if we run into any technical difficulties or small failures, we ask for your patience and please stick with us. We'll get them sorted out as soon as we can. Our speaker this evening is Dr. Alex Gardner, a research scientist at the Jet Propulsion Laboratory. He earned a degree in engineering from the University of Saskatchewan and a PhD in earth science from the University of Alberta. He is a contributing author to the United Nations Intergovernmental Panel on Climate Change's Fifth Assessment Report. Alex is a member of the NASA Sea Level Change, ISAT-2, NISAR, and GRACE science teams and studies the Earth's cryosphere, or frozen Earth, with a particular focus on glaciers and ice sheets and their impacts on sea level rise and water resources. Hi, Alex. Thanks so much for joining us this evening.
Hey, thanks so much for having me. This is great.
We're so excited to have you. Can you tell us, how did you get involved in this research? And let's start with image number 1, please.
Yeah, so I guess I might not have the most direct route that people would envision. I grew up in Canada. That's why you heard all the Canadian universities there in the intro. I grew up on Vancouver Island, actually, very beautiful place. But, you know, I grew up with my own challenges. My parents divorced when I was quite young. And I grew up with a learning disability. So I learned to speak late. I learned to read late. And it was a big challenge kind of early in my childhood. And I went on and, went through high school and some stuff was pretty easy for me, like physics and math, but I always struggled with English and anything that involved language. And I guess I didn't really have strong ambitions to pursue a degree. And then decided that maybe, engineering would be a good fit for me. And kind of in my second year of engineering, I realized I had a talent. I had a talent for maths. And I realized that it was maybe something that it was a skill that I could really use to help the world. So I had thought for a while of what it was that I wanted to be my contribution, and I wasn't too sure. So in my second year of university, I went down to South America for a year with my wife, and we just traveled around. And at one point, I found myself in the tip of South America. In a place called the Puerto Moreno Glacier. And I watched the sun come up over this glacier, and I was just in awe as this thing started to break up and calve off into the ocean. And actually, that's the image on the right there, is sitting in front of that. I kind of had this epiphany that this is so much energy and mass held in these systems, and I kind of wondered if anyone had ever studied it. And so after that, I went away and I started to think about pursuing a postgraduate degree, a PhD, and just was wondering if there's anybody that studied this type of stuff and what the impact of future climate might have on it. And lo and behold, there's a lot of people that study this, and it has a real importance for future climate. And
I was just going to say, that's an incredible start to your journey. Tell us a little bit more about your secondary education, and let's bring up image 25, please.
Yeah, so I got to go to the ends of the earth for my PhD studies. And so we flew up to a place in far northern Canada called the Devon Island Ice Cap. And it was a flight from Edmonton, where the Edmonton Oilers are, up to Yellowknife, which is in the far north, where Ice Road Truckers starts. And then we'd fly to another northern community, which was a native reserve. And then we'd fly to even another northern community, which was our base. And we would base out of there, and we'd fly another 4 hours onto the ice cap. And the plane would have skis, and it would land on the ice. And it was kind of a Dancing with Wolves moment, where all the equipment is pushed out of the plane, and we're just kind of left to set up our camp and do science for 6 weeks at a time, doing shallow ice cores, validating satellite data, making GPS measurements. And every once in a while, we'd have a helicopter come for support, so we could access some of the more difficult parts of the glacier. But it was really eye-opening to see, how much of our planet is actually covered by ice. So most people probably have never heard of the Devon Island Ice Cap, but it's 14,000 square kilometers, and it's not even one of the larger ice caps. We have huge amounts of ice at the poles. We have the Greenland ice sheet and the Antarctic ice sheet, and they lock up, almost 90% of all the world's fresh water. It's huge amounts of water stored in these things, but we don't live near them, so we don't think about them that often and their importance.
I think we can all see from the beautiful images that you have displayed just how beautiful ice is and how you got attached to studying this. But can you tell me, why is it important to study ice, and what's the motivation really to study it?
Yeah, so I think for me, it started off as a bit of a nostalgia. And as I became more and more involved and really took it on in the PhD, you realize its importance. So the world has been covered by large amounts of ice in the past that have waxed and waned. So much so that when it was about 4 degrees colder in North America, we had what was called the Laurentide ice sheet 20,000 years ago. And that ice sheet was so massive that it came all the way down and covered Boston and Chicago with about a mile of ice. And it created Cape Cod. And then as the climate warmed, that ice mass retreated. And that actually created a land bridge at the time, because sea levels had dropped so much because there was so much land on ice. And people were able to move across the land bridge from Asia into North America. And it impacted the climate, it impacted the sea levels, and it even impacts the rotation of the Earth. So believe it or not, when you have more ice caps, there's more ice at the poles, you put more mass at the poles, which actually causes the Earth to spin a little faster. And when you lose that ice, it actually it kind of sloshes down towards the equator. And it's kind of like a ballerina putting her arms out when she's spinning. If she puts her arms out, she puts her arms out to slow down. And so as the ice melts, it actually slows the rotation of the planet. It's shaped a lot of the landscapes that we see. It's responsible for all sorts of really interesting things. And it's one of the most vulnerable to a changing climate. And that's because ice on Earth resides very close to 0 degrees Celsius. So right near the melting point. So you turn up the thermostat just a little bit and a lot of things change. And not only that, but they've got these amazing, what we call feedbacks, where if you push it a lot, it starts to run away. And it has some of the largest feedbacks in the Earth system. And they're fascinating as a researcher to study, and highly important in terms of what the societal consequences of those things mean.
It's good to understand that the ice is important. I know you wanted to walk us through video 11, so let's go ahead and pull that up now, and you can explain a little bit about what's going on there.
Yeah, so Let me give a little bit of an intro before we go to image 11 here. So the ice sheets are always gaining mass and always losing mass. So since the dawn of time, an ice sheet has always had snow falling on it, and it's always had water running off into the ocean. And when the climate is in equilibrium, there's always as much coming in as there is going out. And so the geometry of the ice sheet stays the same. And so it's this amazing thing where the ice sheet's always in balance. It's always putting ice into the ocean, and it's always getting snow from accumulation. But as you turn up the thermostat, you start to move things out of equilibrium, and two things happen. So first of all, you get what you would normally expect, and that is that the water runs off into the ocean. So you melt the surface melts, and all that water runs off into the ocean. But the thing we think about a little bit less is the ice is moving, it's dynamic. And so the image that you see here, the movie that you see here is absolutely spectacular. This is just a single calving event. And a calving event is that ice in the background that you see. It's flowing down slowly into the ocean. And when we talk about future sea level rise and future sea level rise uncertainty, it's this part that we're interested in, this part that we're most concerned about, because that ice can start to slip. And so in this image, what you see is this massive piece of ice calve off in the background. And that person in the tent, they've been waiting there for days to capture this calving event. And you see him come out of the tent just before the calving event occurs. He's coming out because he hears the cracking and he's wondering what's going on, but he doesn't see anything yet, and then runs out with his camera to take pictures. And that's a single iceberg. This happens quite frequently. That iceberg would be almost a mile thick and probably about 1.5 miles wide. And when that thing calves off, it releases so much energy that the seismometers in continental United States can pick up those events. So you can actually see the earthquakes that this thing generates when that big calving event rotates off. And so it shows you how much power and mass these ice sheets are moving around. And so I just say one more thing, and that is that when we see the ice sheets change, when the topography or the elevation, or when we start to see changes, what that tells us is that the climate that they exist in is no longer in balance with them. And so the ice sheets have to respond. They have no choice. And so this is where NASA comes in and brings in a large suite of tools.
So tell us about those tools. What are NASA scientists doing to study ice and climate?
Yeah, so NASA's doing all sorts of really amazing things. Maybe we could bring up the first image of the ICESat 2, and I'll talk about that satellite. So I'm just going to nerd out here for a bit. I am not a closet nerd. I am totally out of the closet. I am 100% nerd, and I love this stuff. And this is some of the coolest engineering that we can imagine. So this instrument that you're looking at here is called a laser altimeter. Now, it is no different than that thing you go by at the hardware store to tell you how far you are from one wall. It shoots out the little infrared beam and you can measure the distance. Well, this is a much more sophisticated version of that. And so it has a laser. That laser goes out and it splits into 6 different beams when it goes through a special lens. And those 3 beams land on the Earth. And it releases trillions of photons with each shot. And it takes 10,000 shots per second. So it's operating incredibly fast. And each one of those shots lands on the surface of the Earth. And those trillions of photons scatter all over the place. And only 6 to 12 of those photons end up reaching the telescope back on the spacecraft. And it can time tag each individual photon. So the smallest quanti of energy, we can now measure it bouncing off the surface of the Earth. And we can make incredibly precise measurements of how the surface of the Earth is changing. So for an example, I'm in Los Angeles. And if you were standing on the sidewalk in San Diego, which is all the way down at the Mexican border, I could measure whether you stepped off the curb or not. That's how powerful this thing is. So that instrument, what it allows us to do is it allows us to see the shape of the ice sheet as it responds. So we might see it growing, we might see it shrinking in response to either a warming ocean, changes in precipitation, or changes in warming from the atmosphere. And so it tells us a huge amount about what the ice sheets are doing in response to current changes in climate. And the other satellite I wanted to talk about, if we could bring up image 23. And this one's just as fascinating. This is a follow-on satellite, meaning we've done this once before. But I used to be a professor in Massachusetts, and I taught remote sensing, which is basically satellite observations. And the start of all of those textbooks says, satellites measure some spectrum of the electromagnetic spectrum. And that was true until we put up GRACE. So GRACE is actually measuring changes in the Earth's gravity. And so, you probably learned in school that gravity is 9.14 meters per second squared. Well, it actually has slight variations everywhere on Earth. And where there's more mass, like a large mountain, the gravitational pull is ever so slightly higher. And so these satellites orbit the Earth, and as they do, they very precisely measure the distance between themselves, down to the fraction of the thickness of a human hair in distance between those satellites. And it goes around and it repeats these measurements. And so we can actually see where the gravity is stronger and where the gravity is weaker. But even more amazing is it can see the changes over time. And so when it rains in California, we can see California get heavier because there's all this water sitting on the surface. But the biggest changes that we see are the ice sheets. The ice sheets are rapidly losing mass into the oceans. And so we can see that in incredible detail on a monthly resolution. So we can actually see these things gain mass in the winter and then lose a whole lot of ice in the summer. And it's fascinating. The engineering that's being done, I don't think is imaginable even 20 years ago.
It really is a miracle of engineering. And, NASA's studying these things, not just from space, like you've talked about, but we're studying ice from using planes, from the ground, with ice cores. But what have we learned from all this great engineering?
Yeah, that's a great question. So let me just start with the satellites, and then I'm going to put the satellites into a bit of a broader perspective. So the satellites have really revealed a lot of things. They've revealed some concerning things in the Antarctic. There's very vulnerable places in the Antarctic. Specifically, it's Pine Island and Thwaites glaciers. There's these two larger than you can imagine streams of ice that pour ice from the interior of the ice sheets into the ocean. And those two systems are particularly vulnerable to what we call the marine ice sheet instability. And that is where you start melting, you start putting, the ice flows faster, it puts more ice into the ocean, that causes it to melt faster. And there's this feedback loop, and you can get these runaway effects where the ice sheet collapses. And we don't know if that's happening. There's some speculation that it is happening. And I don't even know if we have a consensus on that, but the satellites reveal that it is changing now. And so it's an area that we're looking at a lot. It's revealed that the East Antarctic is gaining a little bit of mass. And then it's also revealed that since about 2000, the Greenland ice sheet has been rapidly losing mass as we've had much warmer Arctic summers. But we've unfortunately only had a really short record from space. And so there have been people with boots on the ground that have been taking all sorts of measurements. And probably one of the most valuable measurements that we have is ice cores. And so this is where they take a drilling rig and they bring it to the ice sheet, and it's a huge, huge operation. And they spend years drilling these long cores of ice, and trapped within the ice are tiny little bubbles that were actually trapped from the atmosphere all the way up to 1 million years ago. And so you can take that ice and you can bring it, seal it up and bring it back to a lab, and you can actually extract the air that's in those bubbles. And so we can see what the past concentration of greenhouse gases was in the atmosphere in incredible detail for the last 1 million years. So I'm going to bring up a figure here, figure 17, and this is just a great example. So here's a record from one of the ice cores, and it goes back almost 1 million years. So I'm showing 800,000 years. And to put that into perspective of how long that is, I've marked on this figure where the birth of modern man was about 200,000 years ago. So modern man has existed for a climate that's kind of been within these wiggles ever since modern man was on Earth. And it's just incredible the information we can get. So the red one that we see, that is a proxy for temperature. It's a fraction between delta 018 and 016. But what it tells us is it tells us how much energy or what the temperature was of the atmosphere all the way to 800,000 years ago. And then the other thing we can measure directly is the amount of CO2 contained in those air samples. And as you can see in this figure, as the CO2 goes up, so does the temperature. And when the CO2 goes down, so does the temperature. And so they follow each other incredibly well. And there's all these complex feedbacks that we understand that are, very difficult to, anyway, there's a lot of processes involved, but the only thing that matters is that, the temperature of the planet is incredibly closely tied to the amount of greenhouse gases, and in this case, CO2 in the atmosphere. And I've plotted two other things on the right-hand side of that figure. You can see the concentrations of CO2 in the atmosphere in 1940. So we call that the pre-industrial level of CO2. And then I've also marked to scale on there what the measurements were from satellites from 2017. And we know that those satellite measurements are really accurate because we validate them with all sorts of measurements from the ground. And this has taught us a lot, and it's been fascinating to study as a glaciologist. But it's also kind of terrifying. And I say that in the most sincere way because I started my career in glaciology in 2005, and there wasn't a lot happening to the ice then. And usually when we would think of glaciers, we would think of glaciers as responding really slow to something. And we used to say it happened at glacier timescales, which meant it happened really slowly. And even 10, 15, 20 years ago, people kind of thought that it would take a while for the ice sheets to respond once the climate changed. But what we started to learn is there were some processes that we didn't understand fully, and the ice sheets are responding really fast. And so just over this short period, we've seen really rapid changes in the ice sheet. We see the Greenland wasting away, putting almost 250 cubic kilometers of water into the ocean every year, causing measurable amounts of change in sea levels. And the glaciers, every glacier region on Earth is losing mass. So it's losing ice into the ocean. So Alaska, Patagonia, high mountain Asia, the Alps, New Zealand, all of the Arctic islands, everywhere there's ice, it's all being wasted away, which tells us that the ice is out of equilibrium with the climate. And that's a lot to digest, and we've learned a lot more about the systems. But what brings it all into perspective is this next slide. This next slide shows where we're expected to be at by the end of the century. So that's only 80 years from now. So there's people that are in cribs right now, or possibly in kindergarten, that will still be alive when we hit these numbers. And I've shown 3 dots on that graph, and this is to scale. And it takes a minute to digest, but the one best estimate there, the blue dot there, that says peak emissions in 2030, that is a probably over optimistic scenario. I mean, that right there, sorry, 2040, not 2030. That right there is, if we really got our act together as a people on this planet, and we were able to stop or to have peak emissions by 2040, we would have a 3 degrees Fahrenheit rise in temperature, and concentrations of CO2 would be as indicated on that graph. If we have peak emissions in 2060, which is still considered overly ambitious at this point, considering the progress that we've been able to make so far, we would have a 4 degrees rise in temperature. And if we just kind of operate like we're operating right now, and since this study came out in 2005, all indications report that we are on this higher track. It is the best prediction of what track we're on right now. And this is what we call the business as usual. So if we start to account for improvements in technology that will slowly bring down the emissions, improvements in fuel economy, if we assume that the poor countries will want to have lifestyles more similar to developed Western nations, first world nations, if we account for these things, and then we also account for the plateauing of population growth, as we expect that population growth will peak during this century. This is where we'll be at. And again, that small figure at the bottom, that is the variability over the last 800,000 years. And what I'm showing to scale is the different scenarios of where we're headed. And so when I do the science I'm doing, I'm only studying the very bottom part of that graph. And when we look at the models to tell us what does it mean when we look at these future scenarios, they tell us that there's a lot of negative consequences coming down the pipeline. They tell us that the ice is going to continue to melt. That's a guarantee. And they tell us that the wetter regions of Earth will likely get wetter. The drier regions of Earth will likely get drier. The frequency of storms and droughts will increase. And then there's some other impacts as well. Rising oceans will start to cause problems for coastal communities where we've built a lot of our infrastructure. And so I don't want to be a complete doomsday person. I mean, there are things we can do to mitigate this. And the best thing that we can do to mitigate this is really to focus on the emissions. And so really, we're going to have to stop emitting greenhouse gases into the atmosphere. And whatever we can do to get towards that path is positive. But whatever it is, it's going to have to be collective action. And so we're far beyond the point now of being able to do individual action to have a meaningful impact on this situation. It is very serious, and it is something that we need to tackle starting now. And we're also going to have to think about mitigation now. We're not just talking about avoiding any harm. Some harm is already going to happen. We already have enough CO2 in the atmosphere that we're going to have to think about mitigation. And so that is, thinking about our coastal infrastructure and which infrastructure we would like to shore up and defend against a rising ocean, which infrastructure it probably isn't cost effective to do that. And what that means is that we have to spend taxpayer dollars on mitigating this. And the most effective use of taxpayer dollars is really to prevent it from going in the atmosphere in the first place. Because once you start trying to kind of mitigating all the compounding consequences afterwards, it gets really expensive. And I'm sure we would rather spend our tax dollars on healthcare or any of the other number of things, or just keep it in our pockets than spending it on mitigating the damage we've done. Yeah. So I listened to a very prominent scientist this morning, and he said, let's be the generation that rose to the challenge, not the generation that failed to rise to the challenge.
That's a great way to put it, Alex. And we've talked about the consequences. We've talked about moving forward, but I think the audience is really engaged. So I want to give Jocelyn a chance to ask some of those questions for our viewers. Jocelyn, how's it looking out there?
Lots of great questions coming across all of our social media platforms. We have Pei Chow on Facebook that asks, is there a relationship between ice and extreme weather? And how will extreme climate affect the future?
Wow, that is a great question. And yes, there are very strong links. There is an interesting thing that they believe happened in the past, and that is that there was so much water that poured off of the Laurentide ice sheet that it actually put a freshwater cap in the North Atlantic. And that freshwater cap prevented what we call the thermal haline circulation, which is how the oceans move, how the oceans circulate water. And at the time, it actually prevented it, and it caused a very cold Europe. And people are studying this in a lot of detail. And there is a real risk that could happen. I think the risk of it happening is unlikely, but there is a risk that it could happen. But most of the extreme comes from changes in precipitation. So we have a stronger gradient between the polar regions and the lower latitudes, and that drives a much more vigorous climate. And so that's where we expect a lot of the extreme drought and extreme precipitation to come from.
Let's go with another question from the audience, Jocelyn.
Yes, Corey on LinkedIn asks, has the quality AI images changed over the duration of your career?
Oh, it's incredible. The engineering advances are phenomenal. So I was born in 1980. So the first kind of Earth satellite was launched. Really was the first Landsat satellite, kind of in the mid 1970s. So not much before I came around. And in the 1970s, the military was flying satellites. Flying satellites as part of the Hexagon missions. In the 70s, they were taking pictures with film and ejecting those, deorbiting the canisters of film, and then picking those up with planes. And so the quality has changed immensely. I mean, I bring up that data because I use that data in my research because it's the only record we have. It's the one that goes furthest back is this military record from the 70s. And you could imagine they were catching this stuff with planes and then developing it on Earth in a darkroom. And so we've just seen a rapid advancement in our ability to observe the Earth.
It's great to hear that we've had that advancement. I'm sure there's lots more questions. Jocelyn, what else are they asking for Alex?
You mentioned earlier how we use ice to look into the past, and Tim on YouTube asks, what is the date of the oldest ice that's being studied?
Wow, that's a great question. So we have that very detailed record all the way back 800,000 years, but they're going back millions of years in some of the ice cores. But the problem is that ice is so old and it's so deep that it's all been squished and squashed right at the bottom of the ice sheet. And so it's a real challenge to get the data out of there. And so they actually have other ways they look even further back in time. And so one of the ways they look further back in time is you could imagine that when the Earth is drier, there can be more dust storms, and that dust can deposit over lakes. And so we can actually go and take these lake cores and we can see back millions of years, and we can see records of drought and flooding. We can see, we can look at the isotopic record. We can even go into the deep ocean and take mud cores from the bottom of the ocean. We can look at these tiny little creatures called diatoms, and they tell us the concentrations of different gases and what the environment was like back in the day. And we can also see sediment records from when the Greenland ice sheet was last gone. And so we can see a gap in the record where there stopped being any of the glacial deposits being put out by the glaciers. So there's all these different ways we can look back in time to understand the past climate.
I'm so glad we've had so many advancements. Jocelyn, go ahead. I'm sure they're itching out there to ask Alex some more questions.
They are. You've mentioned a lot of really interesting data, and Kayla Schneider on Facebook asks, what does this mean as far as being helpful? How can this data help?
So that's a great question, and it's one I struggle with myself. This data is incredibly helpful. It tells us what the Earth system is doing. It tells us all of the complexities about how all of these different parts interact. When you raise CO2, you warm the ocean. When you warm the ocean, you increase the melting of ice around the Antarctic. When you increase the melting of ice around the Antarctic, you cause less ice to resist the flow of ice into the ocean. And so you actually see the ice speed up. And then when you see the ice speed up, you actually see the gravity change. And when the gravity changes, you can see the ice going into the ocean, and then you can see the sea levels rise. And then you can see where the sea levels are rising as the gravity redistributes that ice around the world. It's these observations from space that are the only way we can see the Earth as a complete system, right? It is really a self-contained small ecosystem, a marble in space. And the only way we can understand all of the interconnectivity is through these satellite observations. But I preface that with I struggle. And the reason I struggle is because it's only useful if we can take the science and we can learn from it. And the science has clearly shown over the last 2 decades that the ice is incredibly sensitive to changes in temperature, and it is responding now. And we know that it's going to keep increasing sea levels into the future. And we know a bunch of other things that are going to change in the climate system, most of which, the vast majority of which are going to be negative for most societies. There are some countries that will benefit in the short term. So places like Canada will have increased agricultural productivity. That's a benefit to them, but they'll also have to deal with the increased stresses of other countries having less. And so increased global food insecurity is going to be one of the biggest future consequences. And so the data is really only useful if we use it. If we listen to the scientists that interpret the data, we listen to the modelers that project the future, and then we take that information and we start to think deeply as a society, what are the decisions that we would like to make to include the information that we get from this incredible sensor array that we have in space.
I think we've got time for about 2 more questions.
We have a really interesting question from Curtis on Facebook who wants to know, are there any risks for substantial methane release from undersea storage as it gets warmer? And has this view changed with modern studies?
Yeah, that's a big question. This is obviously a very well-educated listener. Yeah, it's a real thing. So there's this methane that's trapped in the Arctic, and it's encased and frozen in permafrost. And the fear is that it's mostly under the Arctic Ocean, that if the Arctic Ocean warms enough, that the layer that's trapping all of that methane would thaw and give access of the methane to the atmosphere. And that would cause a huge belch into the atmosphere of methane. And now methane's a different beast than CO2. CO2 has a residence time in the atmosphere of about 2,000 years. So if you drive your car and it emits CO2 into the atmosphere, it's going to last for about 2,000 years until it starts to come out of the atmosphere. Methane is much shorter lived in the atmosphere, but it's much more potent. If I remember correctly, I think it's on the order of about 10,000 times more potent as a greenhouse gas. And so if that methane leaks into the atmosphere, it would cause a short-term acceleration to climate, which then could ignite some other feedbacks. But I think the probability is low, but people are studying it in a lot of detail. So it's a concern to scientists. I think they think the probability is low, but it's not impossible.
And we've got time for one last question this evening.
Michelle on Facebook wants to know, how quickly does this information come in that we're getting? And in relation to time, how fast does that happen?
That's a great question. So we have some satellites that are designed for disaster response. And NOAA has satellites that are designed for weather. Those types of satellites, the data has to come back really quick, has to get analyzed, has to go through all the supercomputers to turn the raw measurements into data that people can interpret. And that can go out within hours. A lot of the data we work with, it has to be incredibly precise. And so the first satellite I showed was that ICESat-2 satellite. And we're talking about, centimeter precision on all of these different things. And you need to know the position of the satellite. So there's a lot of complex things that need to be known from other satellites as well, from the GPS network and a bunch of other stuff. And there's a lot of computation that has to be done. And so typically we see that data, within 2 to 3 months, it's on my desk as a scientist.
It's good that you can get the information out, Alex. That was all the time we had for questions this evening, although they have been great questions. Thank you for all of those that are watching this evening. I do want to give our speaker, Alex, a chance for one last final word. And let's go ahead and pull up image 14.
Yeah, so thank you so much for taking the time and listening. And, I really hope that you're able to relate kind of to what we're doing here and, kind of the career path that got me to where I am. I did not ever think I would be sitting at a desk at NASA or in my home during a pandemic either. And I just want to say that sometimes I get quite apathetic about the research, and that's because the research is only useful if we can act on it. And we don't need any more research to know the actions that we should take. And the action is simply that we need to start taking climate change very seriously. And we need to start acting now, and we need to act collectively. And so it's these kiddos in the picture here, my lovely daughter and my wonderful son, that when I have their picture on my desk, I just think that We really need to focus our attention on making right by them and rising to the occasion. We've done it before. We've put a man on the moon. There's no reason we can't arise to this occasion as well.
Incredible sentiment to leave us on. So that's all the time we have for today. Join us next month for our lecture entitled Space Cameras, A Sharper Image. I want to thank our speaker, Alex Gardner, for joining us and discussing this very urgent topic. Thank you. Also, thank you to our wonderful questions co-host, Jocelyn Arqueta, and everyone working behind the scenes to make this all possible. To all of you watching, thank you for taking the time to join us each and every month. If you've missed one or would like to revisit any of our Von Karman talks from the past 5 years, they are available on JPL's YouTube page. Be well, have a wonderful evening, and we'll see you in May.